Hey class, this is the monumental case here. This is a very important date, very important type of problem that we're going to be talking about. So for 15.5, this is the first time that we're actually going to do an equilibrium problem that's an ice problem. You're going to hear ice several times. I'm going to say it over and over again. You're going to get sick of hearing it. I apologize about that, but we should know what the ICE stands for. ICE stands for you guys making a grid that is initial, change, and equilibrium. And I'm going to show you how to use this and what kinds of problems we need to use the ICE, like the ICE is the way that we solve them, and how do we use the ICE grid then? So this is the type of problem where we're going to be calculating K. If we do not have K from the information, and all we have are some kinds of like maybe initial concentrations, and in this case here we have one equilibrium concentration, which is actually very, very nice. It's going to make our calculations a lot easier. So we're going to start off with an easy ICE problem. I'm going to show you how to do it. So you're going to have to make, like you would start off, I should actually just show you this from the beginning. This right here that you're looking at, this grid right here, is an ICE chart. The ICE chart has initial concentrations for the reactants given here. We know that before the reaction starts, initially there is zero product formed because we have not even started reacting the H2 and the I2 yet. So what's going to happen here? The reactants are going to decrease in concentration. We know that. And it's all based on the number of moles. And I keep saying moles all the time because they're that important. You guys know that the coefficient in front of H2 and the coefficient in front of I2 are both ones here for it to be balanced. That means that I'm going to subtract some amount from H2, and I'm going to subtract exactly the same amount from I2 because they are equivalent mole-wise. It's 1-to-1 ratio between the two reactants, which means that I have a minus X and a minus X. So mole-wise, it's going to be the same amount subtracted. So over here, we're going to add, obviously it's going to be a positive, which you don't have to write the plus down if you don't want to. But notice this. Notice that there's a 2 coefficient in front. So whatever I'm going to add to the products is going to be 2x. It's going to be twice that amount. Okay, that 2 comes down here in front of the x, the part that we don't know. So right now, I'm looking at 1.00 times 10 to the negative third minus some amount is going to be the equilibrium amount for H2. Okay, 2.00 times 10 to the negative third minus x is going to be the amount for I2. Okay, all I did was take these two, the top block and the second block here, and just put them together. Okay, so the top block, second block, put them together to equal this. So this is equilibrium on the very bottom. Now we know what the equilibrium concentration is here for the product. So that was discovered for us, that was tracked, that was measured, and that was given to us. Okay, so that equilibrium concentration for the product is a huge help to us because basically what I have now is a situation, let me get some more room, is a situation where I basically have 2x equals this amount of concentration. Okay? And all of these numbers in here should be concentration. Okay, I talk about moles, but moles, concentration is based on moles. And we're going to assume that it's like equal volume because if you remember, concentration is equal to the number of moles over volume. So we're just going to assume the V is constant, does not change. That's all taking place in the same chamber. And that means that my concentration increases when my moles increase, and blah, blah, blah. So how do I find X then? I'm still looking for the X here and the X here. So how do I find the X? Obviously, according to algebra, I'm going to divide both sides by 2. That means that the X amount that I'm looking for is going to be X divided by that. Okay, so if you're looking on page 645, this is sample exercise 15.9. And on the left-hand side, they do go on to explain what's going on. Now, they use a little different formula to explain how to get the X part, but it all comes to the same thing though. I got 0.935 times 10 to the negative third concentration, okay? Or you can, of course, move it one place over like this and take one away there. So it's 9.35 times 10 to the negative fourth for the concentration, for the molarity, okay? So that's my X. So what is my equilibrium? My equilibrium concentration of H2 would, of course, be 1.00, times 10 to the negative third. This is the board screwing this up, so I'll just keep it like this, times 10 to the negative third. That way, when we get a number for this, it's going to be already in times 10 to the negative third. So that looks like it's going to be 0.065 times 10 to the negative third concentration. Okay, that would be 6.5 times 10 to the negative fifth when I move the decimal place over two places. Okay, that's what our H2, our equilibrium H2 concentration is. Okay, our I2 would be exactly the same thing, except here I'm going to times 10 to the negative third minus 0.935 times 10 to the negative third. So that means what that's going to equal then is going to be where are we at here? 1.065 times 10 to the negative third. And that would be my concentration then for I2. Let me just check to make sure that I did those calculations correctly. So, excellent. If you look at the bottom where they added the new stuff in the blue, they got the same thing that I did. Okay, now all we have to do, now here's the relatively easy part. The ice chart is usually pretty complicated to figure out, and I'll show you some more examples of that, of course. But then once I have the equilibrium concentrations here, which I do for I2 and H2, and I already have it here for HI, then I just go back and do my Kc, which is HI squared over H2, and the concentration of I2 on the bottom, like that. Now all I have to do is plug in the numbers that I have. So I have 1.87 times 10 to the negative third squared divided by the H2 is 0.065 times 10 to the negative third, and the I is 1.065 times 10 to the negative third. And we just add, we multiply all of those, we square the top, and then multiply the bottom and divide the two. So once I'm done with that, then I should get a number that looks very close to 51. Okay, and that's the K value. That equals the Kc for this equation. And I found the K value that by using the ice chart. Remember, if you're looking for the equilibrium constant, then you have to use an ice chart. ICE stands for initial, change, and equilibrium. Okay, that's my example. So we'll do more work with this, much more work.